So students, in the last lecture we had discussed about the distribution ratio and the distribution coefficient. Definition of the distribution ratio and the distribution coefficient. What is the distribution ratio? It is denoted by the symbol Kd. When the solute distributes itself between the two immiscible phases in contact and in equilibrium with each other, then the ratio of concentration of solute between the two phases is constant at constant temperature. This is the distribution coefficient. This also be known as partition coefficient, right? Or distribution coefficient. This distribution coefficient is independent on concentration of a solute, right? But it is dependent on the temperature. That means temperature should be constant. Solution should be dilute. The two solvents should be immiscible to each other, and the molecular state of the solute should be remains constant. That is, no association, no dissociation, or no polymerization should be taking place, right? While the term distribution ratio, which is denoted by the symbol D, capital D, is nothing but the total concentration of a solute between the two phases which are in contact with each other. The ratio of total concentration of solute in organic layer to the ratio of total concentration of solute in aqueous layer. That is called distribution ratio, right? Now, in this lecture, we want to discuss about the relationship between distribution ratio and the distribution coefficient, right? To understand the relationship between them, we have to consider the example. Just say, taking example of a benzoic acid, I write here the short form of benzoic acid as H.B.Sc, right? If we assume that, concentrate on this word, right? If we assume that there should be no association, no dissociation, or no polymerization of benzoic acid in aqueous as well as in organic layer, say ether layer, then I can write the distribution coefficient of benzoic acid, which is equal to Kd, which is equal to Hbz in ether, say organic layer, while Hbz in aqueous layer, that is organic and aqueous layer are in contact with each other, right? Just say this is example or expression number 1, right? Now, suppose I want to find the value of Hbze. From this equation, I can write here Kd into Hbza. This is equation number 2. This is important one, right? If there should be no association, no dissociation, or no polymerization, then I can write Kd is equal to D. This is the relationship between them, right? So very easy to find out relationship between them. That means in distribution coefficient and in the distribution ratio. If no association, no dissociation, or no polymerization, that is molecular state of the solute remains constant, right? But in practice, solute undergo association or dissociation or polymerization. That means molecular state of the solute is not a constant in any one of phase which are in contact with each other. Then in that case, this relation or this expression is not valid, right? So we assume that benzoic acid undergo dissociation in aqueous layer as, that means this Hbz undergo dissociation as H plus and Bz minus in aqueous layer. From the dissociation reaction, I can write here equilibrium constant or a dissociation constant, right? For this benzoic acid in the aqueous layer, so that I am writing here Ka, which is equal to H plus into Bz minus divided by Hbz, right? From this relation, I can find here aqueous layer, and the aqueous layer, right? I can find Bz minus aqueous layer, which is equal to Ka into Hbz aqueous layer divided by H plus. This is equation number 3. This is also important. We will use in the next equation, right? Okay. Up to this you can understand. I am writing here some basic things, right? Now, suppose this benzoic acid undergo dissociation reaction. Then from due to the dissociation of the benzoic acid in aqueous layer, I can write the distribution ratio. Right? Distribution ratio is equal to काय? Total concentration of HBZ in organic layer, say ether, right? Divided by total concentration of HBZ in काय? Aqueous layer. We know that total concentration, that means benzoic acid remain as it is, molecular state is a constant in the organic layer, therefore I can write here HBZE, right? Divided by total concentration of HBZ in aqueous layer, what is? Say here reversible reaction, that means some benzoic acid undergo dissociation while some remain as it is in the undissociated form. Therefore total concentration is HBZ in aqueous layer plus BZ minus in the aqueous layer. This is the total concentration of benzoic acid, that means partially dissociated and partially undissociated. Now this is the distribution ratio of the benzoic acid, okay, in ether and in aqueous layer, which are in contact with each other, and obviously they are immiscible. Say equation number 4. In this equation number 4, we have HBZE, total concentration of benzoic acid in ether layer. We have this value from the equation number 2, right? In the denominator, we have BZ minus ion, okay? And this total concentration of BZ minus ion is in the equation number 3. So, in equation 4, that is distribution ratio, can also be written as, instead of the total concentration of benzoic acid in ether layer, I use equation number 2, that is KD into HBZ into A, that is concentration of benzoic acid in aqueous layer, right? While in denominator HBZ A as it is, concentration of benzoic acid in aqueous layer, while the concentration of dissociated benzoic acid in aqueous layer value is taking from equation number 3. Therefore, Ka into HBZA divided by H plus, concentration of H plus, right? Taking HBZA, that is concentration of benzoic acid in aqueous layer, common from numerator and denominator, cancel each other. We get distribution ratio at the numerator, only distribution coefficient is remain, right? Here concentration of benzoic acid in aqueous layer, here also concentration of benzoic acid in aqueous layer, taking common, and from numerator and denominator that value is a cancel out. Therefore 1 plus Ka upon H plus. This is the relationship between the distribution ratio and the distribution coefficient. Okay. Now here applying some condition, right? Condition first. Okay. If I say that concentration of H plus ion is far greater than K, that means solution is acidic, right? If this situation is achieved, then this value is so much small, right? 1 plus that small value is approximately equal to 1. Then we can say that D is equal to KD, right? Nearly equal to, I am saying that D is nearly equal to KD. Okay. This means solution of benzoic acid remain mostly undissociated and give large value of D, right? We get the large value of D, right? Condition second, suppose I choose the condition second. In the condition second, suppose, okay, concentration of H plus is far less than K, okay. Then if such kind of a condition is achieved, then D will be very small, right? D will be very small, because this K value is a large. 1 plus K value having some approximation value of K, KD upon that value, that means D is a small, so we can say that D is a very small. D is very small. In that situation, D is a very small. Okay. Now, if D is a small, that means distribution ratio is a small. Therefore, extraction of benzoic acid is also small. Right? This is the actual relationship between distribution ratio and the distribution coefficient. Okay, distribution ratio is equal to distribution coefficient upon 1 plus dissociation constant upon H plus ion concentration. Right? And these are the two different conditions, condition first and condition second. Okay, I hope you can understand. So, good day all of you.